6 billion light-years away, James Webb locked onto something that made scientists go quiet. A structure so large it shouldn't exist. A gravitational shape that curves space around it like a fist. And inside it, an energy signature that matches nothing in our models, nothing in our textbooks, and nothing we have ever seen before. We are going to travel through what Webb found, layer by layer. From the first strange signal, to the collapsed ancient filaments, to the cold, dark core that may be rewriting how we understand the universe itself. If you enjoy what we uncover together, subscribe and keep watching. Because what comes next is not something you forget. Take a breath. We launch into the deep. It started with a number that didn't fit. Astronomers running routine deep field scans with James Webb were cataloguing galaxies in a region of space roughly 6 billion light-years from Earth. Standard work. The kind that fills databases, not headlines. But buried inside the data was a gravitational reading that stopped one researcher mid-sentence. The mass signature was too large, not slightly off, not a rounding error. It was the kind of discrepancy that makes a scientist put down their coffee and read the number again. What Webb had detected wasn't a galaxy. It wasn't a cluster of galaxies. The shape of the gravitational field it was measuring stretched across a region so wide that comparing it to anything familiar would almost be insulting to the scale. Think of the distance between your city and the farthest city you've ever visited. Now, imagine that distance means nothing, that it would vanish inside this structure like a single grain of sand dropped into an ocean. That's the kind of scale we're dealing with. Webb didn't find this structure by accident. It found it because of what makes it unlike any telescope before it. Its infrared instruments pierce through clouds of gas and dust that block ordinary light, letting it see further back in time and deeper into regions of space that were previously invisible to us. When Webb locked onto this region, it wasn't just looking at where things are now. It was seeing the light that left this area billions of years ago, and that ancient light was behaving strangely. Light from galaxies behind the structure was bending, slightly, subtly, but consistently. That kind of bending happens when mass is present. Huge mass, the kind of mass that warps the fabric of space itself. Scientists call this gravitational lensing, and Webb caught it happening on a scale that, according to our current understanding of how the universe is built, should not be possible in that region of space. The team that first flagged the anomaly ran the numbers 3 times. Then they passed the data to a second group, then a third. Each time, the result came back the same. Something enormous was sitting in that patch of deep space, bending light, pulling at nearby galaxies, and generating a gravitational field that matched no known object or structure in any existing catalogue. The word structure was used carefully at first. Scientists are trained to be cautious. A structure implies shape, implies boundaries, implies something organized enough to be defined. Calling this a structure meant committing to the idea that what Webb found had a form, that it wasn't just a diffuse smear of mass scattered randomly across space, but the data kept pointing in one direction. The mass was concentrated. It had edges, it had a center, and it had something inside. That detail, quiet at first, buried in a footnote of the initial report, would become the reason the entire scientific community eventually turned its attention to this corner of the sky. Because mass alone is unusual, but a structure with something inside it, something generating its own signal, that's a different conversation entirely, and that conversation was just beginning. The word massive gets thrown around constantly. A massive storm, a massive sail, a massive crowd. We've drained it of its power through repetition, turned it into background noise. So let's rebuild it from scratch. Let's put real weight back into that word. The structure Webb detected spans a region of space that, if you tried to cross it, traveling at the speed of light, would take you longer than the entire current age of human civilization. multiple times over. You would be born, live your entire life, and die, and the journey wouldn't be close to finished. Your children would face the same fate, and their children, generations upon generations of travelers, none of them ever reaching the other side. That is what massive means here. To give your mind something to grip, consider the Milky Way. Our galaxy contains somewhere between 100 billion and 400 billion stars. It stretches roughly 100,000 light years across. It is, by any reasonable measure, an enormous thing. The structure Webb found dwarfs the Milky Way, the way a mountain dwarfs a pebble. Now, consider that our galaxy is not alone. It belongs to a group of galaxies called the Local Group, which spans roughly 10 million light-years. The Local Group sits inside a larger structure called the Virgo supercluster. The Virgo supercluster sits inside an even larger one called Laniakea, which stretches about 500 million light-years across and contains the mass of 100 million billion stars. Most people, hearing that, assume we've hit the ceiling, that Laniakea must be close to the largest thing there is. It isn't. The structure Webb locked onto appears to operate at a scale that rivals or exceeds the largest known cosmic structures ever confirmed. Structures like the Hercules Corona Borealis Great Wall, which stretches roughly 10 billion light-years across and represents the upper limit of what our models say should exist. Structures that large challenge a core principle in cosmology called the cosmological principle, which states that at large enough scales, the universe should look roughly the same in all directions, with matter spread evenly rather than clumped into enormous formations. When something gets big enough, it starts to break the rules, and what Webb found may be sitting right at that breaking point, or past it. Here is the part that makes this more than just a size competition. Large structures exist. Scientists have catalogued them. What makes this one different isn't purely its scale. It's the combination of scale with organization, with defined edges, with a measurable center, and with what appears to be a concentrated source of mass sitting inside it. Size alone is strange, but a structured, organized, enormous object with something generating gravity from its core, that stops being a matter of scale. That becomes a question of origin. Where did something like this come from? How did it form? And what has been sitting at its center, bending light and pulling at galaxies for potentially billions of years? The answers start with understanding how Webb sees, because without that, none of this would have been found at all. Every telescope is blind to something. The human eye sees a narrow slice of light. Radio telescopes hear a completely different part of the spectrum. X-ray observatories catch high-energy radiation invisible to everything else. No single instrument sees the full picture. Every one of them is looking through a specific keyhole. James Webb was built with a very particular keyhole in mind: infrared light. Infrared sits just beyond what human eyes can detect. We feel it as heat, but in space, it carries something more valuable than warmth. It carries information from places that ordinary visible light can never reach. Clouds of gas and dust that block starlight for thousands of light years are nearly transparent to infrared. Webb cuts through them the way sunlight cuts through fog. This matters enormously for what it discovered. Between us and any object 6 billion light years away, there is a lot of material. Dust clouds, gas filaments, ancient galaxy halos, vast regions of diffuse matter floating between galaxies, too thin to be visible, but thick enough to scatter ordinary light. For decades, anything hiding behind this cosmic haze was simply invisible to us. We knew it existed because of indirect signals, but we couldn't see it. Webb changed that. Its primary mirror, nearly 2 stories tall, is made of 18 hexagonal gold-coated segments working together as a single surface. Gold, specifically, because it reflects infrared light better than almost anything else. The mirror gathers light across a surface area about 6 times larger than Hubble's. In astronomy, more surface area means more light collected, and more light means seeing fainter, older, more distant objects. Webb also orbits our star at a point called Lagrange 2, about 1 million miles from Earth, on the side away from our star. This keeps it shielded from solar heat, which would otherwise interfere with its sensitive infrared detectors. Sitting there in the cold dark, far from Earth's warmth, Webb can detect temperature differences smaller than a fraction of a degree. This sensitivity is what made the discovery possible. The gravitational lensing signal from the structure was faint. The light bending around it came from galaxies almost incomprehensibly far away, distorted by fractions of a degree that no previous instrument would have registered. Webb caught it because it was cold enough, sharp enough, and precise enough to see what everything before it missed. But there's something else worth understanding about how Webb sees time. Because light travels at a fixed speed, looking into deep space is always looking into the past. When Webb observed this structure 6 billion light-years away, it wasn't seeing what exists there today. It was seeing what existed there 6 billion years ago. The structure, as it was, halfway back to the beginning of the universe. That means whatever is inside it, whatever is generating that mass signature, existed long before Earth formed, long before our star ignited, long before the solar system was anything more than a cloud of dust. Webb didn't just find a structure, it found a relic, and relics always carry history inside them. Before the structure had a name, before it had a confirmed shape or a measured size, it had a signal. One signal. Quiet. Persistent. Wrong. Gravitational data coming from that region of space showed a lensing pattern that didn't match what should be there. When astronomers map a region of deep space, they have a rough expectation of how much mass is present based on how many galaxies they can count, how bright they are, and how those galaxies interact with each other. The observed mass and the calculated mass usually stay close. Not perfectly, because dark matter adds invisible weight, but within a predictable range. In this region, the numbers were far outside that range. Gravitational lensing works like a glass lens. When light passes near something massive, space itself curves, and the light follows that curve. The result is that background objects appear stretched, duplicated, or bent into arcs when seen from Earth. The degree of bending tells astronomers how much mass caused it. More bending means more mass. Precise calculations let scientists work backwards from the bend to estimate what's out there. The bending pattern Webb recorded was too strong, by a significant margin. The visible galaxies in that region could not account for it. Dark matter, the invisible material that makes up the majority of mass in the universe, was factored in using standard models. Still, not enough. The numbers kept pointing to a concentration of mass that had no visible source, no bright galaxy sitting at the center, no known object emitting radiation from that location, just gravity, pulling, bending, existing. Scientists use a term for this kind of discrepancy: a mass excess. It sounds dry, clinical, but what it means in practice is that something is there that shouldn't be, or that something is there that we don't have a name for. The first pass at the data flagged it as a possible instrument error. Webb, like any tool at the edge of human engineering, is not perfectly immune to artifacts, small false signals created by the instrument itself rather than the universe. The team ran calibration checks. They compared readings from different detector segments. They isolated the signal and tested it against known noise patterns. The signal was real. A second observation was scheduled. Webb turned back to that patch of sky and gathered more light, more data, more time. The lensing pattern came back, stronger now, because more observations allowed for a cleaner picture. The mass excess was confirmed, and with the higher resolution of the second pass, something new emerged. The mass wasn't spread evenly across the region. It was organized, concentrated toward a center, surrounded by a broader field but clearly anchored at a specific location in space. That's when the word structure started being used in the internal reports. Carefully, hesitantly, but consistently. A diffuse cloud of dark matter would have a soft, gradual mass distribution. This had edges, definition, a gravitational architecture that suggested something built, or at least something shaped by forces that acted with intention over an enormous span of time. The signal wasn't noise. It was a message the universe had been broadcasting for billions of years. And finally, something was listening closely enough to hear it. The first email about the anomaly was forwarded without much fanfare. That's often how paradigm-shifting discoveries begin. Not with a press conference or a moment of collective gasping, but with a quiet note passed between researchers that says, essentially, "Can you look at this and tell me I'm wrong?" The astronomer who flagged the signal initially assumed there was a simpler explanation. A foreground galaxy cluster, perhaps, one sitting between Webb and the distant background, massive enough to produce strong lensing on its own. That would be unusual, but not impossible. Or a calibration artifact, an error in how the data was processed, rather than a genuine feature of the universe. The reply came back. There's no foreground cluster. The lensing doesn't match that pattern. A third researcher joined, then a fourth. Within a few weeks, a small informal team had formed around the question of what, exactly, was sitting 6 billion light years away and bending space with far more gravity than anything visible could explain. What followed was months of quiet, meticulous work. This is important to understand, because the popular image of scientific discovery tends to involve dramatic moments. The eureka, the shout, the champagne. Real discovery usually looks different. It looks like long hours rerunning the same calculation with slightly different assumptions to see if the answer changes. It looks like searching existing catalogues to see if anyone else noticed this region before. It looks like writing careful, heavily qualified sentences that say we think rather than we know. By the time the team was confident enough to circulate a draft paper, roughly 18 months had passed since the first flagged signal. Every alternative explanation they could construct had been tested and ruled out. The mass excess was not an artifact. It was not a cluster hiding in the foreground. It was not a statistical anomaly in a small dataset. It was real. It was large. It was structured. And it had something at its center. The draft paper landed in the scientific community the way a stone lands in still water. First, a small ripple of response from the researchers who review these things before publication. Then, as word spread to broader circles, a wider reaction that mixed genuine excitement with the kind of skepticism that good science requires. Several prominent voices pushed back. The mass excess, they argued, could still be explained by exotic dark matter behavior that standard models don't fully capture. The structure's edges might be an artifact of how the data was processed, rather than a real feature. The signal at the center might be a coincidence, an alignment of unrelated objects along the same line of sight. These were fair challenges, reasonable ones, but they couldn't explain all of it. Every time a critic proposed a simpler explanation and ran the numbers, something didn't fit. The data kept resisting the ordinary, and when the paper was formally published and the broader astronomical community turned its attention to that patch of sky, the skepticism didn't disappear. It just shifted from whether the anomaly existed to what, exactly, it was. That question would prove far harder to answer than anyone expected. Describing a cosmic structure is harder than it sounds. There is no photograph that captures it. No image Webb has taken shows a clean, crisp shape floating in the dark, the way a planet or a galaxy might appear. What we have instead is a gravitational map, a picture drawn not with light, but with the bending of space itself. And that picture, once assembled from Webb's data, shows something genuinely strange. The structure is not spherical. Most large accumulations of mass in the universe trend toward roundness over time. Gravity pulls material inward from all directions, and given enough time, things become roughly ball-shaped. This structure doesn't follow that pattern. Its gravitational footprint is elongated, stretched along one axis, compressed along another. The shape, in rough terms, resembles a flattened spindle or an enormous lens, wide across the middle, tapering toward two ends. This matters because shape carries information about origin. A structure that looks like this was likely not shaped by simple inward collapse. Something guided its form. Either the original material it formed from had a specific geometry, or some force acted on it from outside, compressing it along one axis while it expanded along another. Neither of those options is ordinary. The overall extent of the structure, measured by the reach of its gravitational influence, spans a region that takes light an enormous amount of time to cross. But the most active, most densely massed region sits in the interior, a roughly central zone where the gravitational signal peaks, where the lensing is strongest, and where whatever is generating the anomalous energy signature appears to be concentrated. Picture a fog bank over the ocean. Most of the fog is thin, spread wide, barely visible. But at the center of the bank, the fog thickens. Visibility drops to almost nothing. The density there is dramatically higher than at the edges. The structure behaves similarly. Most of its mass is distributed broadly, but at the core, something is packed much more tightly. Around the edges of the structure, astronomers have identified what appear to be older galaxies, some of the earliest star systems Webb has catalogued in that region of sky. They don't sit randomly. They appear to follow the shape of the structure, clustering preferentially along its elongated axis, as though they were drawn into position by the structure's gravity, or as though they formed along it the way crystals form along a crack in rock. This arrangement is called a preferred orientation, and it suggests the structure didn't form after the galaxies did. The structure came first. The galaxies organized themselves around it. That sequencing is deeply unusual. In standard cosmological models, structures form because galaxies already exist, and their mutual gravity draws them together over time. This structure appears to have preceded the galaxies near it, which means it formed from something other than galaxy-scale material. It formed from something older, something that was already there when the universe was young and the first stars hadn't yet ignited. What that something was, and what remains of it at the core, is where things take a sharp turn into territory that has no comfortable explanation. Empty things don't pull. That sounds obvious, but it's worth saying plainly. Gravity requires mass. A region of space with nothing in it exerts no gravitational pull on anything around it. If you removed every particle from a volume of space, that volume would become gravitationally invisible. Light would pass through it in a straight line. Nearby galaxies would feel nothing. The interior of the structure Webb found is not empty. We know this because of what the interior does to the space around it. The gravitational lensing pattern isn't uniform across the structure. If the mass were spread evenly, the bending of background light would be consistent from edge to edge. Instead, the bending is strongest at the center, dramatically stronger, the kind of gradient you would expect if a significant concentration of mass were sitting specifically at the core. Something is in there. The first attempt to characterize it focused on radiation. Whenever matter does anything energetic, whether it collapses, heats up, collides, or falls toward a gravitational center, it tends to emit radiation, X-rays from hot gas, radio waves from spinning magnetic fields, infrared heat from warm material. Webb, with its infrared sensitivity, searched the core region for any emission that could pin down what was generating the gravitational signal. What it found was subtle, almost too subtle. A faint infrared excess, meaning slightly more infrared radiation coming from that region than the surrounding space would produce on its own. Not a blazing beacon, not a bright source lighting up the core like a lantern. something quieter, a warmth that shouldn't be there given how cold and diffused the surrounding space appeared. This faint signal has a technical designation in the research papers, but what it means in plain terms is this: the core of the structure is slightly warmer than it should be if nothing were there, and it is generating that warmth consistently, not as a one-time event, but as a steady output that Webb measured across multiple observation windows. A few immediate explanations were considered and tested. A dense cluster of ancient, dim galaxies could, in theory, produce a combined infrared signal without any single bright source. The team looked for individual galaxy signatures within the core. They found some, but not enough to account for the full signal. The galaxies present were too few and too faint to explain the total infrared output. A second possibility was hot gas, diffuse plasma, heated by ancient gravitational processes and sitting at the center in a thin, spread-out cloud. Hot gas radiates, and if enough of it were present, it could, in theory, produce a faint warmth. But gas that hot tends to also emit strongly in X-rays, and the X-ray data from the region doesn't support a massive heated gas cloud at the core. Each ordinary explanation failed to account for the full picture. The mass was too concentrated, the warmth was too consistent, and both were present in the same location. Something was there. Something that had been there for an extraordinarily long time. And it was not behaving like anything in the catalogue. But why couldn't it simply be empty? Why does physics itself say that's impossible? That's exactly where we go next. Let's stay with the question for a moment. Why can't the center simply be empty? It's a fair thing to wonder. Voids exist in the universe, large ones. The Boötes void, for example, is a region of space roughly 300 million light-years across that contains almost nothing. No galaxies at its center, barely any at its edges, just space. That void has a gravitational profile consistent with emptiness, almost nothing bending light, almost nothing pulling on surrounding matter. The interior of this structure is nothing like that. The gravitational signal from the core is strong, concentrated, directed inward toward a central point in a way that is inconsistent with an empty region. Physics has very clear rules about this. Gravity doesn't generate itself. It is a consequence of mass. Every unit of gravitational force you measure can be traced back to a corresponding amount of mass somewhere. That relationship is not a soft principle or a working hypothesis. It is one of the most tested and confirmed relationships in all of science. So, when you measure the amount of gravity coming from the core of this structure, you are measuring the mass that must be there to produce it, and that mass is not small. Think of it this way. If you hang a weight on a string, the string pulls toward the ground. The heavier the weight, the stronger the pull. You don't need to see the weight to know something is there. The tension in the string tells you. Webb is reading the tension in space itself, and the tension at the core of this structure is significant. Dark matter is the first obvious answer people reach for. Dark matter doesn't emit light or radiation. It interacts with the universe only through gravity. You cannot see it, detect it directly, or observe it doing anything except bending space and pulling on other matter. If a large concentration of dark matter were sitting at the core of this structure, it would produce exactly the kind of gravitational signal Webb measured, with no visible source. This explanation is on the table. It's taken seriously. But it runs into a problem. Dark matter, in every model we have, distributes itself in predictable ways. It clumps, yes. It forms halos around galaxies and clusters, but it also disperses over time. A highly concentrated dark matter core of the scale implied by this structure would, according to our models, require conditions to maintain it that don't naturally exist in that region of space. Something would need to be holding it together. And then there's the infrared signal. Dark matter doesn't emit radiation. It doesn't produce warmth. Whatever is generating the faint but consistent infrared excess at the core has to be something that interacts with light. Something made of ordinary matter, or at least something that generates heat through a process we can in principle understand. An empty structure can't produce that signal. A purely dark matter core can't either. The core of this structure contains something that has mass, something that generates heat, and something that has been sitting there, stable and organized, for billions of years. That combination doesn't exist anywhere else in our catalogue, not quite like this. And what comes next is the story that makes it stranger still. To understand why this structure is so unusual, you first need to understand the shape of everything. The universe is not a random scattering of galaxies. It has architecture, a vast, intricate network of structures that astronomers call the cosmic web. And once you know it exists, you can't unsee it. Picture a three-dimensional spider's web spanning billions of light years. The threads of the web are called cosmic filaments, long, rope-like structures made of gas, dark matter, and galaxies, all strung together by gravity over billions of years. Where multiple filaments cross, matter piles up, and you get the densest regions in the universe, galaxy clusters containing thousands of galaxies packed relatively close together. Between the filaments are the voids, vast empty regions where almost nothing exists. This web-like structure is the large-scale skeleton of the cosmos. It formed gradually. In the earliest moments after the Big Bang, matter was distributed almost uniformly throughout space, but with tiny variations, regions that were fractionally denser than others. Gravity is relentless. Over millions of years, those denser regions pulled in surrounding matter. Over hundreds of millions of years, that matter began to organize into sheets and filaments. Over billions of years, galaxies formed along those filaments, and the cosmic web took on the shape we map today. The longest confirmed filaments stretch hundreds of millions of light years. They are not solid objects. They are more like rivers of matter, thin by cosmic standards, but visible in galaxy surveys because galaxies prefer to form along them rather than in the empty voids between them. Webb has added enormously to our picture of these filaments. Its infrared vision detects not just the galaxies strung along them, but the gas between galaxies, the warm tendrils of material connecting galaxy clusters, and even the early seeds of filament formation in the distant universe. Here is why this matters for what Webb found. The structure sits in a region where the cosmic web should be relatively well understood. At that distance from Earth, we have good maps of the large-scale structure. We know roughly where the filaments are and how dense they should be. The structure Webb detected does not fit neatly into the known Webb pattern. Its scale is too large for a standard filament. Its mass concentration is too tight for the diffuse, spread-out profile of a typical filament. Its elongated shape resembles a filament in outline, but the internal structure, particularly that concentrated core, is something filaments don't have. A filament is like a highway. Matter flows along it. Galaxies line up along it. But no highway has a city of this size sitting at its center. No filament, as currently understood, has a concentrated mass anchor at its midpoint, generating a distinct gravitational and infrared signal. The cosmic web is the context, but this structure breaks out of that context. It plays by different rules, or possibly by older ones, rules that governed the universe before the web had fully formed. And that older universe, the early one, is exactly where the next clue lives. Every field of science has a standard model. In cosmology, it's called lambda CDM, which stands for lambda cold dark matter. It is the framework that describes how the universe formed, how it evolved, and how the large-scale structures we see today came to exist. It is not perfect, but it is extraordinarily well tested. Decades of observations of the cosmic microwave background, galaxy surveys, and gravitational measurements have all confirmed its core predictions to remarkable precision. And then Webb came along. Webb was not designed to break the standard model. It was designed to see further, see clearer, and fill in the details of a picture the model had already outlined. But detail, it turns out, has a way of revealing cracks. Lambda CDM makes specific predictions about what large-scale structures should look like at any given point in the universe's history. It predicts how massive they can be, how dense they can be, how organized they can be, and how early in the universe's history they can form. These predictions are not loose. They are grounded in calculations that account for the rate of expansion of the universe, the density of dark matter, and the behavior of gravity across billions of years. The structure Webb found exceeds those predictions in ways that are difficult to accommodate. Start with its mass concentration. At the distance Webb is observing, the standard model does not predict a structure with the level of central mass concentration seen at the core. The model allows for large structures at that distance, but they should be looser, more spread out, still organizing themselves, still in the process of formation. A tightly organized structure with a defined center and a concentrated interior mass suggests a formation timeline that is too fast for Lambda CDM to comfortably explain. Then there is the shape. The elongated, spindle-like geometry of the structure raises questions about what forces shaped it. The standard model's predictions for large-scale structure formation tend to produce rounder or more irregular shapes at these scales. A structure with clean, defined elongation suggests either unusual initial conditions or a process of formation that the model doesn't fully account for. And then there is the signal at the center. Lambda CDM has no ready-made explanation for a stable, concentrated mass with an infrared excess at the core of a structure this large. The model describes how mass accumulates, but what would cause it to organize into a warm, compact anchor at the center of a billion light-year scale structure remains outside the model's current scope. Scientists are careful not to declare the model broken based on a single observation. The standard model has survived many challenges, and it will likely survive this one in some modified form. Anomalies are often resolved by adjusting parameters rather than discarding the framework entirely. But some anomalies can't be resolved that way. Some anomalies require a new piece of physics, a new ingredient, something that was absent from the original recipe. What that new ingredient might be is exactly what the leading theories now attempt to answer. And the first of those theories reaches back to the very beginning of everything. What comes next is even older than you expect. Before galaxies existed, the universe was a different place. Not dark exactly, not silent, but formless in the way that matters most. There were no structures yet, no stars, no clusters, no web, just an ocean of gas and dark matter, stretching in every direction, almost perfectly smooth, with tiny ripples of density variation running through it, like the surface of a pond after a stone has been dropped. Those ripples are called primordial density fluctuations. They were seeded in the first fraction of a second after the Big Bang, imprinted into the fabric of space by quantum processes operating at scales almost impossibly small. And they are the seeds of everything that came after. In the standard picture, those ripples grew, slightly denser regions pulled in surrounding material. Over tens of millions of years, sheets of gas and dark matter began to form. Those sheets collapsed into filaments. Those filaments became the threads of the cosmic web, and galaxies formed along them. But the standard picture assumes a certain rate of growth, a pace of collapse, a timeline. What if, in certain rare regions, the conditions were different? The leading theory for the structure Webb found proposes that what we are looking at is a megapilament, a primordial structure that formed during the earliest phases of the universe, when conditions allowed certain overdense regions to collapse much faster and much more completely than the standard model typically permits. In most regions of the universe, primordial filaments are long gone. They collapsed, fragmented into galaxies, and dissolved into the web. Their original identity as unified filaments was erased billions of years ago. But in regions where the initial conditions were unusually dense, or where the surrounding expansion of space happened to be slightly slower, a filament might have survived. Not as a gas structure, which would have dispersed long ago, but as a dark matter skeleton, a gravitational remnant holding the outline of its original form. The elongated, spindle-like shape of the structure fits this picture remarkably well. Primordial filaments were not spherical. They were stretched along the directions of least resistance in the early density field, compressed along others. The aspect ratio of what Webb found, wide across the middle and tapered at the ends, matches what theoretical models predict for a collapsed megafilament viewed from a specific angle. The mass concentration at the center is also consistent. As a filament collapses inward under its own gravity, material flows toward the midpoint. The center of a collapsing filament becomes the densest region. If the collapse was complete enough and ancient enough, that central mass could have been sitting there for billions of years, largely stable, while the galaxies that formed around it slowly orbited its gravitational anchor. The infrared signal from the core remains harder to explain under this theory, but not impossible. Ancient populations of dim stars or compact objects could, in principle, generate faint warmth without being detectable as individual sources. The megafilament theory is elegant. It works within the framework of known physics, even if it stretches the parameters, but it requires a competing theory to fail, and the competing theory refuses to go quietly. The megafilament theory is tidy. It fits inside the boundaries of what we already know. It asks physics to stretch a little, but not to break. The rival theory asks physics to break, or at the very least, to make room for something it has never formally encountered before. The rival theory begins with the infrared signal, not as an afterthought or a minor puzzle to be explained away, but as the central piece of evidence, because here is what the megafilament theory struggles with. A collapsed dark matter structure, ancient and stable, should be cold. Not absolutely zero, but not generating a consistent infrared excess either. Dark matter doesn't heat up. It doesn't radiate. It sits there, bending space, doing nothing that would warm the surrounding region. Something at the core of this structure is warm, persistently, measurably. The rival theory argues that what sits at the center is not a passive remnant of the early universe. It is an active source, something generating its own gravitational field and its own energy output. Not a remnant of something that happened long ago, but a process that is still happening now. The class of objects most seriously proposed in this context is something called a quasar remnant, but at a scale and configuration that has no confirmed precedent. Quasars are among the most energetic objects in the known universe. They are powered by supermassive black holes actively consuming surrounding material. In their active phase, they outshine entire galaxies. But quasars don't stay active forever. They burn through their fuel, quiet down, and leave behind a black hole sitting in the dark. Some researchers have proposed that the core of this structure could be the remnant of a quasar-like object of extraordinary scale. Not a typical supermassive black hole sitting at the center of a galaxy, but something operating at a different level entirely. A concentration of mass so great that it has been maintaining a slow, steady energy output for billions of years without exhausting its supply. The numbers required for this are extreme. The mass at the core, if this theory is correct, would far exceed anything in the confirmed catalogue of cosmic objects. It would require a formation mechanism that predates the known population of supermassive black holes and operates on a scale our current models don't describe. That's the part critics focus on. You cannot simply invent a new class of object to explain an anomaly. You need evidence beyond the anomaly itself. You need corroboration from other observations, other wavelengths, other instruments. And this is where the story gets genuinely uncomfortable for both sides. The corroborating evidence is ambiguous. It neither clearly confirms the active source theory nor rules it out. Webb's data shows something warm and gravitationally dominant at the core. It does not, yet, show the specific spectral signature that would definitively identify what type of object is there. Both theories are standing, both are being tested, and the people doing the testing are careful not to commit prematurely, because the history of astronomy is full of anomalies that turned out to be something ordinary, and full of ones that turned out to be something that changed everything. At some point, in any conversation about deep space anomalies, dark matter gets mentioned, usually as the answer, the invisible catch-all that fills in whatever gap the visible universe leaves behind. Dark matter is real. Let's be clear about that. It is not a placeholder or a guess. It is the most thoroughly confirmed, unseen substance in science. We know it exists because of what it does. It bends light. It holds galaxies together. It provides the gravitational scaffolding that the visible universe hangs on. Without dark matter, galaxies would fly apart. The cosmic web wouldn't exist. You wouldn't exist because the gravitational conditions needed to form stars and planets would never have been met. Roughly 85% of all matter in the universe is dark matter. The ordinary stuff, atoms, molecules, every star and planet and cloud of gas, makes up only about 15% of the total mass. We are the minority ingredient. And yet, dark matter cannot explain everything about this structure. Here is why. Dark matter interacts with the universe only through gravity. It does not interact with light in any way. It cannot absorb photons, emit them, or scatter them. It is, to every detector we have ever built, completely invisible except for its gravitational effects. The infrared signal at the core of this structure requires something that interacts with light. An infrared excess means photons are being produced or absorbed and re-emitted at infrared wavelengths by something in that region. Dark matter cannot do this. Whatever is generating that signal is made of ordinary matter, or is a process involving ordinary matter, even if dark matter is also present. So dark matter is almost certainly part of the structure. A significant part. The overall gravitational architecture, the broad mass distribution across the elongated body of the structure, almost certainly reflects a massive dark matter concentration shaped by ancient gravitational dynamics. But dark matter is not the whole story. There's a second problem. Dark matter, in the quantities implied by the core concentration, would, over billions of years, tend to disperse unless something were actively keeping it together. Gravity works inward, yes. But in the expanding universe, regions of dark matter that aren't bound into a stable configuration tend to lose their coherence over cosmic timescales. The core of this structure appears to have maintained its concentration for an extraordinarily long time. That stability requires either an extremely deep gravitational well, meaning an enormous amount of mass packed into a relatively small volume, or some physical process that continues to maintain the concentration against the natural tendency toward dispersal. Neither of these options is something dark matter alone can provide. A deep gravitational well comes from a lot of mass, which still leaves the question of what that mass is. And dark matter has no internal process for maintaining coherence. It simply responds to gravity. It doesn't generate it from within. So, dark matter fills part of the picture, a large part. But the piece it can't fill, the warm, concentrated, stable core, keeps pointing towards something else. Something that has been waiting at the center of this structure since long before our planet existed. And the temperature readings from that region are the next piece of the puzzle. Space is cold, not uniformly cold, not empty of all energy cold. But the background temperature of the universe, the baseline warmth left over from the Big Bang, has dropped over billions of years to just a few degrees above absolute zero. In the voids between galaxy clusters, between the filaments of the cosmic web, temperature readings hover near that floor. Almost nothing. Almost as cold gets. The interior of this structure is not that cold. Webb's infrared detectors are among the most sensitive ever built. They can distinguish temperature variations across regions of deep space that no previous instrument could resolve. When they were pointed at the interior of the structure, particularly toward the core, the readings showed something unexpected. The core region is warmer than the surrounding space by a measurable margin, not dramatically warmer, not glowing with heat the way a star or an active galaxy would, but consistently, detectably warmer, the kind of warmth that tells you energy is being deposited there from somewhere. In astronomy, warmth has sources. A region of space doesn't simply stay warm without a reason. Heat disperses. Energy spreads outward. If something was warm 1 billion years ago and nothing has been replenishing that warmth since, it should be cold by now. The universe is extraordinarily efficient at draining heat away into the surrounding void. The core of this structure is not draining cold. This persistent warmth is one of the most quietly alarming features of the entire discovery, because it implies an ongoing process. Not a historical event, not a burst of energy that happened long ago and left a warm trace, but something that continues to operate in the present, or at least in the present as Webb observed it, which is actually 6 billion years ago from our perspective. At that point in cosmic history, the universe was roughly half its current age. The cosmic web was well established. Most of the galaxy formation that would ever happen was already underway. It was not the wild, energetic, early universe of the first billion years. It was a middle-aged cosmos, settling into its current rhythms, and yet, in this structure, something was still running warm. Several mechanisms have been proposed. Slow accretion of material onto a central compact object could generate heat as infalling gas converts gravitational energy into radiation. A dense population of ancient, faint stars, a kind known as white dwarfs, collectively radiates infrared wavelengths and could in principle warm a region if packed tightly enough. Interactions between dark matter particles, if they have certain exotic properties, might produce a small but persistent heat output. Each of these mechanisms is physically possible. None of them, individually or in combination, fully accounts for the magnitude and persistence of the observed warmth given the size and configuration of the core. The temperature readings don't identify the source. They don't give you a name or a shape or a category. They just tell you, with quiet insistence, that the core is not inert. Something is happening in there. Something that has been happening for longer than our planet has existed, and the light passing near that core is behaving in ways that add another layer of strangeness entirely. Light doesn't lie. It bends, stretches, redshifts, and dims across cosmic distances. But each of those behaviors follows rules, precise, mathematical, tested rules that astronomers use to read the universe like a language. When light behaves unexpectedly, it means something unexpected is out there shaping it. Near this structure, light is doing something it shouldn't. The gravitational lensing we've already discussed is the most dramatic effect. Background galaxies, sitting far behind the structure from our perspective, have their light bent as it passes near the structure's mass. This produces arcs and distortions in Webb's images, and by measuring those distortions precisely, scientists reconstruct the gravitational map of what's bending the light. That reconstruction is where the first anomaly appeared. The lensing pattern near the core is stronger than the surrounding mass distribution would predict, even accounting for the central concentration. The bending is too tight, too focused, as though the mass at the center is more compact than it appears in the broader gravitational map of the structure. A diffuse mass spread across a large volume produces gentle, gradual lensing. A compact mass concentrated at a point produces sharp, intense lensing. The core of this structure lenses light more like a point source than like a diffuse cloud. That's a significant distinction. It suggests the mass at the center is packed into a smaller volume than the overall structure implies. But the lensing isn't the only strange behavior. There is also what astronomers call anomalous redshift. Light from distant galaxies directly behind the core of the structure shows a slightly different redshift than expected based on their estimated distance. Redshift, in most contexts, measures how fast something is moving away from us due to the expansion of the universe. Objects at the same distance should show the same redshift, but light passing close to an extreme concentration of mass experiences an additional effect, gravitational redshift, where photons lose energy climbing out of a gravitational well. The galaxies directly behind the core show a subtle additional redshift compared to galaxies at similar distances elsewhere in the sky. This is consistent with their light having passed through an unusually deep gravitational well at the core of the structure. Deep enough, in fact, that some researchers have noted the measurement falls outside the range expected for a dark matter concentration alone, even a very dense one. This is where the two theories start to diverge most sharply. The megapilament theory can accommodate unusual lensing as long as the dark matter concentration is dense enough, but the gravitational redshift data pushes the required density toward the upper edge of what's plausible for a dark matter structure without a compact object at its center. The active source theory uses this as supporting evidence. A compact object of sufficient mass sitting at the core would produce exactly this combination: concentrated lensing and anomalous gravitational redshift in the light passing nearest to it. The light passing through this region is whispering something. It has been traveling for 6 billion years to reach Webb's detectors, carrying the fingerprint of whatever it passed through. And surrounding that core, the oldest galaxies in the structure tell a history that the light alone can only partially reveal. Not all galaxies are the same age. When you look at the universe today, you are seeing galaxies at many different stages of their lives. Young galaxies, blue with new stars, being born, middle-aged ones, like our own Milky Way, a mix of old and new stellar populations. And ancient galaxies, red and quiet, their star formation long since ended, populated now only by old, cool stars slowly fading toward darkness. The galaxies orbiting the outer edges of this structure are ancient, extremely ancient. Webb's ability to determine the age of a galaxy comes from its light. Specifically, from the spectrum of that light, the pattern of wavelengths emitted by the stars inside it. Young stars burn hot and blue. Old stars burn cool and red. A galaxy's spectrum is essentially a population census of its stars, and from that census you can estimate when those stars formed, and therefore how old the galaxy is. The galaxies Webb found clustered along the elongated edges of the structure are dominated by old stellar populations. Their star formation, for the most part, ended long before the epoch we are observing. They are among the earliest galaxies in that region of the sky to have formed and then stopped forming new stars. This is known as quenching. Galaxies stop forming stars when the gas that feeds star formation is depleted, heated, or expelled. One of the most effective ways to quench a galaxy is the influence of a powerful gravitational source. Strong gravitational fields and the energetic processes associated with massive compact objects can heat surrounding gas, preventing it from cooling enough to collapse into new stars. The ancient, quenched galaxies at the edge of this structure appear to have had their star formation shut down earlier than isolated galaxies of similar mass typically experience. The timing suggests they were quenched by an external influence, something powerful enough to affect their gas supply, and something that was already in place when these galaxies were still young. The structure, and whatever sits at its core, appears to have been present and influential during the earliest epoch of galaxy formation in that region. These galaxies didn't just happen to form near it. They formed in its gravitational shadow and were affected by it while they were still in their infancy. That is a powerful constraint on the timeline. Whatever is at the core of this structure was massive enough and active enough to affect galaxy evolution billions of years ago. It wasn't building itself up gradually over cosmic time. It was already in place, already dominant, already shaping the environment around it. In our current models, Objects that grow large enough to affect galaxy evolution across that kind of distance take a very long time to assemble. The most massive black holes, for instance, are thought to have grown gradually over hundreds of millions to billions of years. But the galaxy quenching pattern around this structure suggests its central mass was already in place and already powerful very early in the history of the universe, earlier, perhaps, than it should have been able to get there. And that timeline problem is exactly what Webb's second observation run brought into sharper and more troubling focus. Science doesn't rest on a single look. After the initial discovery and the publication of the first analysis, the team submitted a request for additional observation time with James Webb. These requests are competitive. Webb's schedule is oversubscribed. Hundreds of scientific programs compete for time on the most powerful space telescope ever built, and not every request is granted. But anomalies of this magnitude tend to move up the priority list. The second observation run was longer. More instrument modes were used. Webb turned its spectrographic tools toward the structure alongside its imaging detectors, allowing it to analyze the light from individual objects in and around the structure and break that light into its component wavelengths. Spectroscopy is where astronomy becomes chemistry and physics. A spectrum is a fingerprint. Every element, every molecule, every physical process leaves a specific pattern in the light it emits or absorbs. By studying those patterns, astronomers can determine what something is made of, how fast it's moving, how hot it is, and in some cases, what's happening inside it. The spectroscopic data from the second run added several new details, none of them simpler than what came before. First, the galaxies at the edges of the structure confirmed what the imaging data had suggested. Their spectra showed old stellar populations and very little ongoing star formation. Their ages were consistent with formation in the very early universe, and the evidence for early quenching was strengthened. Second, the gas detected in the region between the edge galaxies and the core showed unexpected characteristics. Gas between galaxies is usually cool and diffuse, a thin medium called the intergalactic medium. The gas in the interior of this structure was warmer than that baseline and showed spectral signatures suggesting it had been disturbed at some point in the past by a powerful energy event. Not recently, the disturbance was old, but it had left a chemical imprint in the gas that persists. Third, and most significantly, the spectrum of the core region itself showed something that had not been visible in the first run's data. A faint but consistent emission feature at a specific wavelength that didn't match any obvious foreground contamination and appeared to be intrinsic to the core itself. That emission feature is still being analyzed. It does not match the spectrum of ordinary hot gas. It does not match the standard spectrum of an active galaxy or a quasar. It sits at a wavelength that suggests either an unusual chemical composition, an unusual physical process, or an object of a type that has not been formally catalogued. The team's paper on the second run was careful. They did not claim to know what the emission feature means. They reported it as an unidentified spectral line and called for follow-up observations at other wavelengths to characterize it further. Unidentified spectral lines have a history in astronomy. Some have been resolved quickly, others took decades. A few led to entirely new discoveries. Helium, now the second most common element in the universe, was first identified as an unidentified spectral line in the light from our own star. For a while, it was called an unknown element before someone worked out what it was. This spectral line is not helium, but no one yet knows what it is. Here is a number that matters: 13.8 billion years. That is the current estimated age of the universe, measured from the moment of the Big Bang to the present day. Everything that exists has had, at most, 13.8 billion years to form, grow, and become what it is. No star is older than that. No galaxy, no structure, no object of any kind can have existed before the universe itself began. This seems obvious. but it creates a constraint that the structure Webb found is beginning to challenge. We observe the structure as it existed roughly 6 billion years ago, when the universe was about 7 to 8 billion years old. For the structure to show the characteristics Webb measured at that point in time, it must have been assembled significantly before that observation epoch. Structures don't appear fully formed. They build over time, accreting mass, pulling in surrounding material, settling into their final configurations. The ancient quenched galaxies at the edges of the structure, which appear to have had their star formation suppressed by the structure's central mass very early in their lives, imply that the core was already in place and already powerful when those galaxies were young. The oldest of those galaxies formed roughly 10 to 11 billion years ago, when the universe was only 2 to 3 billion years old. This creates a timeline problem. If the core of this structure was already massive enough to quench galaxies across millions of light years roughly 10 billion years ago, then it had to have assembled a significant fraction of its mass within the first 2 to 3 billion years of the universe's existence. 2 to 3 billion years sounds like a long time, but in the context of how the largest structures in the universe are believed to form, it is extraordinarily fast. The most massive objects we know of, supermassive black holes, are themselves pushing against the timeline. Webb has found supermassive black holes that were already enormous when the universe was less than 1 billion years old. And that discovery has been one of the major challenges to existing models. The standard picture of black hole growth through gradual accretion cannot produce objects of that mass that quickly. The core of this structure implies a similar or even more extreme timeline problem. Something assembled a mass concentration powerful enough to reshape the galaxy population around it in a region hundreds of millions of light years across, and it did so within the first fraction of the universe's lifetime. This pushes against two things simultaneously. The standard picture of structure formation, which predicts a slower, more gradual assembly process, and the standard picture of object formation, which has no confirmed mechanism for producing a compact mass of this scale this quickly. One of the most uncomfortable possibilities being considered by a small number of researchers is one that sounds, at first, almost impossible to take seriously. What if the mass at the core of this structure didn't form after the Big Bang? What if it preceded it? That question has a name in theoretical physics, and the answer, if it turns out to be yes, would not just challenge the standard model. It would require us to revise what we think the Big Bang itself actually was. Before accepting that something is genuinely new, science demands you exhaust every ordinary explanation first. That instinct is not timidity. It is discipline. The history of astronomy is littered with anomalies that turned out to have mundane solutions. Strange readings caused by instrument glitches, exotic signals that resolved into ordinary objects viewed from unusual angles, apparent violations of physics that collapsed into simple geometry errors once the data was properly calibrated. The team working on this structure has spent considerable effort doing exactly that, systematically identifying every conventional explanation and testing it until it breaks or holds. The first candidate was projection. Sometimes, objects that appear to be associated with each other in the sky are simply lined up along the same line of sight by coincidence. Two separate structures, one behind the other, can look like a single large structure when viewed from a particular angle. The team tested for this by analyzing the redshifts of all the galaxies and gas detected across the structure. If projection were the explanation, you would expect to find two distinct groups of objects at different distances, overlapping only because of the viewing angle. The data shows a coherent distribution of material at a consistent distance. Projection doesn't explain it. The second candidate was foreground contamination. A massive galaxy cluster sitting between us and the observed region could produce strong gravitational lensing that mimics a structure behind it. The team mapped every galaxy cluster known in that line of sight. None of them, individually or combined, produces lensing consistent with what Webb measured. The lensing is coming from the 6 billion light-year distance, not from anything in the foreground. The third candidate was data processing artifacts. The way Webb's data is converted from raw detector readings into usable images and spectra involves a complex pipeline of calibration steps. Errors in any part of that pipeline can introduce false signals. The team ran the data through multiple independent pipelines and compared the results. The anomalous signals appeared consistently across all of them. The fourth candidate was a known exotic object misidentified. The structure could, in principle, be a gravitational lens of unusual configuration, or a filament viewed end-on, which would make it appear more concentrated than it actually is, or a dense cluster of faint galaxies, too dim to be individually resolved, but collectively massive enough to produce the observed lensing. Each of these was modelled and tested against the data. None of them fit all the observations simultaneously. They each explain some of the data while failing on other fronts. The fifth candidate was statistical noise. In any large dataset, rare alignments and unusual distributions appear simply by chance. The question is whether the anomaly is more extreme than what chance alone would produce. Statistical analysis of the structure's characteristics places the probability of it arising from random fluctuations in the data at a level that the research community treats as effectively impossible. What remains, after all of that elimination, is something the conventional toolkit cannot comfortably explain. Not impossible, not confirmed as entirely new, but persistently, stubbornly outside the range of ordinary explanations. The leading candidates that remain are not conventional. They require either new physics, new objects, or a revision of what we believe happened in the earliest phases of the universe. And the most dramatic of those remaining candidates involves an idea so extreme that even the researchers who propose it do so quietly, carefully, and with every qualifier they can think of. Black holes are the densest objects the universe produces. At their centers sits a point of such extreme mass concentration that the laws of physics, as we understand them, break down entirely. Space curves so severely that nothing, not matter, not light, not any signal of any kind, can escape once it crosses the boundary. We know supermassive black holes exist at the centers of most large galaxies. Our own Milky Way has one, called Sagittarius A star, with a mass about 4 million times that of our star. The largest confirmed supermassive black holes discovered so far reach masses billions of times greater. They are extraordinary objects, but they are, by now, expected. They fit into our picture of galaxy formation, if imperfectly. What the black hole cluster hypothesis proposes for the core of this structure is something different in kind, not just in scale. The hypothesis suggests that what sits at the center is not a single massive black hole. It is a cluster of them, potentially thousands of ancient black holes formed in the very early universe before the first galaxies existed, orbiting a shared gravitational center in a configuration that has remained stable for billions of years. These hypothetical objects are called primordial black holes. The concept is not new. Theoretical physicists have proposed for decades that extreme density variations in the very early universe, fractions of a second after the Big Bang, could have collapsed directly into black holes without ever going through the stage of a star first. Ordinary black holes form when massive stars die. Primordial black holes, if they exist, skipped that step entirely. They formed from the raw material of the early universe itself. Most primordial black holes, if they formed, would be relatively small. The density variations that produce them would typically be modest. But in regions of extreme overdensity, the process could, in theory, produce much larger ones. And over billions of years, those large primordial black holes could have drifted together under mutual gravitational attraction, forming a cluster at the center of a primordial density anomaly. The cluster, not a single object, would explain several features of the data. A distributed mass source, rather than a single point, would produce the broad gravitational footprint observed. The combined mass of thousands of ancient black holes could account for the extreme gravitational lensing and the anomalous redshift of background light. And black hole clusters of this type would generate heat through a process called dynamical friction, where objects moving through a gravitational field lose energy and radiate it, producing exactly the kind of faint, persistent infrared warmth Webb detected. The numbers involved are extreme by any standard. The total mass implied by the gravitational data, if distributed across a cluster of primordial black holes, would require the cluster to have formed from conditions that are beyond the upper range of what standard inflationary models predict. But not infinitely beyond, not impossibly beyond. The primordial black hole cluster hypothesis sits at the frontier of what is theoretically imaginable. It has not been confirmed. It has not been ruled out. It demands new observations, new instruments, and possibly new theory to test properly. And if it turns out to be correct, the implications for everything that comes after in this story reach far beyond astronomy. Because what comes next challenges not just our models of space, it challenges our understanding of time itself. Science is not a collection of facts. It is a collection of the best explanations we have found so far, always provisional, always open to revision when new evidence arrives. That framing sounds humble, and it is, but it also obscures how difficult it is, in practice, to revise a framework that has been built over decades, tested against thousands of independent observations, and woven into everything from satellite navigation to the design of particle accelerators. The cosmological standard model is not just a theory sitting in a textbook. It is embedded in every major observatory's data pipeline. Every redshift survey assumes it. Every measurement of the universe's expansion rate uses it as the foundation. When you challenge a framework that embedded, you are not just proposing a new idea, you are suggesting that a very large number of previously trusted results may need to be reinterpreted. That is exactly what this structure forces onto the table. The challenge begins with formation timelines. The standard model, built on well-understood physics of gravity and expansion, predicts how fast structures of various sizes can assemble. Small structures form first, larger ones form later, built from smaller pieces drawn together over time. This is called hierarchical structure formation, and it is one of the most robust predictions in cosmology. The structure Webb found appears to violate the hierarchy. Something of its scale and central mass concentration should not have been in place as early as the quenched galaxy population implies. It was too big, too organized, too dominant, too early. Webb has found structures like this before, objects that formed too early. Since it began operations, Webb has repeatedly discovered massive galaxies and enormous black holes at distances corresponding to the first billion years of the universe. Each one individually could be explained as a statistical outlier, a rare fluctuation, an extreme tail of the distribution. But the accumulation of such outliers is beginning to look less like coincidence and more like a systematic gap in the model. This structure is the most extreme example yet. If confirmed, it suggests one of several possibilities. Either the early universe produced density fluctuations more extreme than current inflationary models predict, creating the seeds for unusually fast structure formation, or there is a new physical process operating in the early universe that accelerates the assembly of massive objects beyond what standard gravity alone allows. Or the universe is older in some effective sense than its 13.8 billion year age implies, perhaps because of physics near the Big Bang that we have not yet correctly characterized. None of these options is comfortable. Each one requires revising something foundational, not discarding the entire framework, but modifying it in ways that ripple through many other conclusions. The scientific community's response has been predictably divided. Some researchers argue the anomaly will be resolved by a more mundane explanation that hasn't been fully explored yet. Others argue the accumulation of Webb's early universe surprises demands a serious reconsideration of the Standard Model's early universe assumptions. This structure sits at the center of that debate, not as the only piece of evidence, but as the most extreme one. And extreme evidence has a way of being the thing that finally tips a field toward change. Let's follow the thread all the way to its end. Assume, for a moment, that the most extreme interpretation of the data is correct, that the core of this structure is a stable, ancient, extraordinarily massive concentration of compact objects formed in the earliest moments of the universe, predating the first galaxies, and sitting in place for nearly the entire history of cosmic time. What happens to physics? The first casualty is the standard inflationary model of the Big Bang. Inflation is the theory that the universe, in the first fraction of a second of its existence, underwent a period of exponential expansion, expanding by a factor so enormous it makes all subsequent expansion look trivial. Inflation is the leading explanation for several features of the universe that would otherwise be inexplicable. Why the cosmic microwave background looks nearly identical in all directions, why the universe appears geometrically flat, and why the distribution of matter at large scales looks the way it does. Inflation also makes predictions about how large and how extreme the early density fluctuations were. If those fluctuations were too large, they would have collapsed into objects far more massive than what we observe. If they were too small, no structure would have formed at all. The model is tuned to produce fluctuations of just the right scale to generate the universe we see. A primordial object of the mass implied by the core of this structure would require density fluctuations at the upper extreme of what inflation allows, or possibly beyond it. That would mean either the inflationary model needs its parameters revised, or a different version of inflation with different properties needs to replace it. The second casualty is our picture of what black holes are and how they form. If primordial black holes exist in the quantities and masses the cluster hypothesis requires, then black holes are not solely the product of stellar evolution, they are also a product of the raw physics of the Big Bang itself. This would mean the universe contains a population of black holes we have never properly accounted for, distributed across cosmic history, potentially influencing galaxy formation, gravitational wave signals, and dark matter behavior in ways we haven't yet measured. Gravitational wave observatories have already begun finding black hole mergers in mass ranges that are difficult to explain through standard stellar evolution. A population of primordial black holes could account for some of those events. The third implication reaches into the very nature of dark matter. One of the proposed candidates for dark matter has always been primordial black holes, and that idea has been tested and constrained over the years. But if this structure is what the most extreme interpretation suggests, it may require revisiting those constraints with new data. None of this means the standard model is wrong in a way that makes everything else crumble. Physics is more resilient than that. What it means is that certain foundational assumptions about how extreme early density fluctuations were, about where compact objects come from, and about how early the largest structures can form may need to be revised. Revisions in physics are not failures. They are the mechanism by which understanding deepens, but they are also the thing that every generation of physicists before us has found most difficult to accept when the revision challenges what they built their careers on. James Webb does not operate in isolation. It is the crown jewel of a network of observatories, each sensitive to different wavelengths, each capable of adding a different layer of information to any discovery. When something significant enough is found, the entire network turns toward it. That is what has begun to happen with this structure. The Atacama Large Millimeter Array, a collection of dozens of radio dishes spread across a high desert plateau in Chile, began observing the region at radio and millimeter wavelengths. Radio observations are sensitive to cold gas and to the thermal emission of dust, both of which could help characterize what the core region is made of, and whether any of the gas there shows signs of organized motion, meaning rotation or outflow, that would indicate a compact central object. The Chandra X-ray Observatory, which operates above Earth's atmosphere to detect high-energy X-ray light, examined the region for hot gas signatures. X-ray observations are particularly useful for detecting accreting compact objects, which heat in falling material to temperatures that emit strongly in X-rays. If the core contains a massive black hole or cluster of black holes actively consuming material, Chandra should see evidence of it. The European Space Agency's XMM Newton satellite joined that effort, providing complementary X-ray coverage with different sensitivity characteristics. On the ground, the Very Large Telescope in Chile used its spectrographic instruments to study the emission line Webb detected in the second observation run, attempting to characterize its wavelength more precisely and look for any variation over time that would indicate the source is variable, meaning it changes brightness or intensity in ways that could reveal its nature. The results from this multi-wavelength campaign are still being compiled and analyzed, but early indications are consistent with the puzzle remaining unresolved. The X-ray data does not show a bright, obvious, accreting source at the core, which argues against an obviously active massive black hole, but it also shows a diffuse X-ray excess in the region that is not fully explained by the known galaxy population nearby. The radio data shows organized structures in the gas near the core that suggest past energetic events, outflows, or jets of material driven by some powerful central process, now faded and cold, leaving only the structural imprint in the surrounding gas. The combination of these observations paints a picture of something that was, at some point in the past, extremely energetic and has since quieted, a former giant, now dormant, still massive, still gravitationally dominant, still warm enough to register on Webb's detectors, but no longer blazing the way it once may have. If that interpretation holds, it would place the structure's most active period somewhere in the very early universe, billions of years before the epoch Webb observed it. The quenching of the surrounding galaxies would be a remnant of that early activity, a mark left on the neighborhood by whatever the core was doing when it was young and burning. That framing raises a question that no telescope, no matter how powerful, may ever be able to fully answer, because some things happened too far away, too long ago, and too far beyond what light itself can carry back to us. There is a boundary at the edge of the observable universe. It is not a wall. It is not a place where space ends. It is a limit created by time. Light travels at a fixed speed, and the universe has been expanding since the Big Bang. Beyond a certain distance, the light emitted by any object has not had enough time to reach us. That region is causally disconnected from us. We cannot see it, signal it, or receive any information from it. It is as unreachable as the past. Even within the observable universe, there are softer limits. Objects that existed very early in cosmic history have had their light redshifted into extreme infrared or radio wavelengths, stretched by billions of years of cosmic expansion until it becomes almost impossible to detect. Webb pushes this limit further than any previous instrument, but it does not dissolve it. The core of this structure sits 6 billion light-years away. We are observing it as it was 6 billion years ago. To understand how it formed, we would need to observe it as it was 10 billion years ago, 12 billion years ago. When whatever process assembled, it was still underway. We cannot do that directly. The light from those earlier epochs, if it carries information about the formation of this specific structure, has either not yet reached us, has already passed us billions of years ago, or has been diluted and redshifted beyond any instrument's ability to detect. This is a fundamental limit, not a technological one, a physical one. Certain questions about this structure may therefore remain permanently unanswered. We can measure it as it was 6 billion years ago with extraordinary precision. We can model what it might have looked like earlier using theoretical frameworks. We can compare it to other structures and use those comparisons to constrain our models. But we cannot see it being built, and the nature of what sits at the core presents its own barrier. Black holes, if that is what is there, are by definition information destroying from the outside observer's perspective. Whatever history they carry, whatever conditions they formed under, is sealed behind an event horizon that light cannot cross outward. The interior state of a black hole is as inaccessible to us as the epoch in which it formed. This matters not just for this structure, but for the broader questions it raises. If the early universe produced objects of this kind, and if those objects carry in their properties the fingerprints of conditions that existed in the first fractions of a second after the Big Bang, we may never be able to read those fingerprints directly. What we can do is measure effects. We can count the gravitational waves produced when primordial black holes merge. We can map the large-scale structure of the universe and compare it to models with different early universe assumptions. We can build better telescopes and look at more objects and accumulate statistics that inch our understanding forward. But the inner history of what Webb found, the precise conditions of its birth, the nature of the process that built it, and the full story of what it did to the galaxies around it during the universe's first few billion years, those things may remain beyond the edge of what any instrument we can build will ever reach. That is not a failure. It is the honest shape of the universe we live in. In 1950, physicist Enrico Fermi sat down to lunch with a group of colleagues and asked a question that has never fully gone away. If the universe is so large, so old, and so full of stars, where is everyone? The Fermi paradox is the name given to the apparent contradiction between the high probability of intelligent life existing elsewhere in the universe and the complete absence of any confirmed evidence that it does. Decades of radio telescope searches have turned up nothing. Every signal has resolved into a natural source. The sky, when listened to carefully, sounds empty of anything made by minds. Many explanations have been proposed. Maybe intelligent life is extraordinarily rare. Maybe civilizations tend to destroy themselves before they can communicate across interstellar distances. Maybe communication methods we haven't thought of yet are being used. Maybe the distances are simply too large and signals too faint for us to have detected anything yet. What this structure adds to that conversation is subtle but worth sitting with. The universe is enormous, 13.8 billion years old, and if what Webb found turns out to be a genuine example of a structure that formed faster than current models allow, in a configuration that has no fully explained origin, then our picture of what the early universe was capable of producing may be incomplete. An incomplete picture of physical possibilities is also an incomplete picture of what environments might have allowed life to emerge, persist, and develop over timescales longer than we typically imagine. We tend to think of the early universe as hostile. It was hot, it was turbulent, it was filled with radiation. The first billion years are not usually considered a promising era for life. But if structures of this scale and complexity could form within the first few billion years, if stable, massive gravitational anchors existed that could influence the evolution of surrounding galaxies and concentrate material in unexpected ways, then the range of environments the early universe produced may have been broader than we assume. This is speculative, enormously so. The connection between what Webb found and the question of life elsewhere in the universe is indirect and uncertain. Finding a large, strange structure does not tell us anything directly about biology or intelligence. But the Fermi paradox ultimately rests on assumptions about how the universe works and what it is capable of producing. Every discovery that challenges those assumptions adds a new variable to the equation. If the universe's early chapters were stranger, more complex, and more productive of unusual structures than we thought, then the space of possible histories, including histories that might include life of some kind, grows larger. the silence of the sky remains. No signal has arrived. No confirmed contact has been made. But the silence is heard against an increasingly unfamiliar backdrop. A universe that can build something like what Webb found, at the scale and speed the data implies, is a universe we understand less completely than we thought we did. And in that gap between what we expected and what we found, every unanswered question, including the oldest one, gets a little wider. Something is out there. We just don't know what it is. James Webb was built to look backward in time. That was always its primary mission, to see the first galaxies, the first stars, the first structures that formed after the Big Bang, to push human vision to the edge of the observable universe and fill in the chapters of cosmic history that previous telescopes couldn't reach. It has done that, and it has done it better than most of its designers hoped. But it has also done something its designers didn't plan for. It has found things that the story, as we understood it, didn't have room for. The structure we've been following through these chapters is the most extreme example. But it is not alone. Webb has found massive galaxies that formed too early, black holes that grew too fast, galaxy clusters that assembled before they should have had time to. Each one individually might be explainable. Together, they are beginning to form a pattern. The pattern says, the early universe was more efficient at building structure than our models predict. The question Webb is now asking, the one that its data is pressing against with increasing insistence, is why. Two broad answers sit at the frontier of current research. The first is that the physics of the early universe, particularly the properties of dark matter and the behavior of gravity at very early times, was different in ways our models don't yet capture. Not different in a way that breaks everything, but different in a way that accelerated certain processes, gave gravity a head start, allowed things to collapse and organize faster than the standard picture allows. The second answer is more radical. It proposes that our understanding of the very beginning, the inflationary period, the nature of the Big Bang itself, is missing something fundamental, that the seeds from which everything grew were not the smooth, nearly featureless fluctuations inflation predicts, but something more complex, more structured, more extreme in certain regions, that the universe was handed unusual initial conditions in some locations, and this structure is one of the places where those unusual conditions left a permanent mark. Neither answer is yet confirmed. Both are being taken seriously. Both would, if verified, require rewriting portions of the textbook that generations of cosmologists have considered settled. Webb will keep looking. Its operational lifetime is estimated at 20 years or more. In that time, it will gather more data on this structure, on the unidentified spectral line, on the ancient galaxies orbiting its edges, and on whatever the multi-wavelength campaign eventually reveals about the nature of the core. Other telescopes being planned will add to the picture. The extremely large telescope, currently under construction in Chile, will have a mirror nearly 40 meters across and will be capable of spectroscopic observations Webb cannot match. The Nancy Grace Roman Space Telescope will survey wide fields of deep space and potentially find similar structures elsewhere that could be compared to this one. The answer is not here yet, but the question has never been sharper. 6 billion light years away, something sits in the dark, massive, old, warm, organized, bending light, shaping galaxies, generating a signal no catalogue explains. And James Webb, floating cold and patient in the dark, a million miles from Earth, keeps watching. Whatever is out there has been waiting billions of years to be understood. We are only just beginning to look.